So let's start by looking at an example of how to infer probabilities given a Bayes network. So this is a famous example from Judea Pearl. Suppose that I'm at work and a neighbor John calls to say that my alarm is ringing, but my neighbor Mary doesn't call. Now, sometimes my alarm is set off by minor earthquakes, so the question is someone breaking into my house? Now, we can represent this with 5 variables. So the variable B will be true if somebody's breaking into my house and false otherwise. E will be true if there's an earthquake and false otherwise. A will be true if there's an alarm going off and false otherwise. J will be true if John calls and false otherwise. And M will be true if Mary calls and false otherwise. So here we have our 5 variables. Now, the Bayes net, or the topology, the structure of the graph that we'll draw, is going to represent common sense or causal knowledge we have about the situation. So, for example, we know that a burglar can set off the alarm, but also that an earthquake can set off the alarm. Similarly, we know that the alarm can cause Mary to call, and the alarm can also cause John to call. So here's a representation of this situation. So we see that there's these two events, burglar and earthquake. Now these are going to be assumed to be independent. They are independent events. And the alarm can be caused by either the earthquake or the burglar, somebody breaking into my house. Both of those could be causes for the alarm going off. Similarly, the alarm could cause John or influence John to call, and the alarm could also cause Mary to call. Now, the green tables here are the conditional probability information. This is the probability information we need to infer any other probabilistic information about the situation. So the burglar and the earthquake are assumed to be independent, so we just have to provide the prior probability of somebody breaking into my house or there being an earthquake. And let's just assume there's a very low probability that somebody's breaking into my house and a very low probability that there's an earthquake. Now, what about the alarm going off? Well, the alarm going off depends on whether or not there's a burglar or an earthquake. And so we're going to represent that using this table. So we write down all the logical possibilities. So B and E could both be true. B could be true. E could be false. B could be false. E could be true. Or they could both be false. And then we represent the various conditional probabilities. So the first row is the conditional probability that the alarm is going off given that somebody's breaking into the house and there's an earthquake. The second row is the probability that the alarm is going off given that somebody's breaking into the house, but there's no earthquake. And the last row, for example, is the probability that the alarm is just going off given that nobody's breaking into the house or there's not an earthquake. So the alarm is going off by accident. There's some type of malfunction. So that probability, of course, is going to be very, very low. Now, one thing I want to flag here, notice that these probabilities here do not sum to 1. So these tables right here are not stochastic truth tables, but that's because the probabilities assigned to each row are not the probabilities that the rows happen, or the probabilities how likely it is that that B is true and E is false, or B is true and E is true, and so on. These are conditional probabilities. These are probabilities that the alarm is going off given that, say, B is true and E is true. And we represent the same information for John calling and Mary calling. But here, John calls in response to an alarm going off. So we just have to represent the situation that John calls given that the alarm is going off, or the probability that John does not call given that the alarm is going off. Now notice, of course, John calling depends indirectly on there being somebody breaking into my house. But we don't need to represent that information directly. That is actually inferred given all of this information. We just represent the probability of John calling given the direct influence, which in this case is the alarm going off. Now, what we want to know is what is the probability say that John calls, Mary doesn't call, the alarm is going off, but there's nobody breaking into the house and there's no earthquake. So what is that joint probability? Now we can read off what this probability is given the Bayesian network. So the first bit of information is what's the probability of J? Well, we know that J depends only on A, so we can read off the probability of J given A directly from this table. So that's going to be 0.9. The probability that John calls, given that the alarm is going off, because we're assuming A is true. So the probability of J given A is 0.9. What about the probability of not M? Well, we know that M depends on A, so we can look at the conditional probability table. We've assumed that A is true, so we're in the first row of that table. But we want to know what's the probability that M is false. Well, the table tells me that there's a 0.7 chance that Mary will call if the alarm is going off. That means there's a 0.3 chance that Mary will not call, given that the alarm is in fact going off. And now we're assuming A is true, but B and E are both false. That means we're in the last row of this table. So the probability that the alarm is going off, but B and E are both false is 0.001. And then we're looking at the probability that B is false and E is false. These are independent, so we just write down those prior probabilities. It's going to be 0.99 and 0.998. And that's because we're assuming B is false. There's a 0.001 chance that B is true, so there's a 0.999 chance that B is false. Multiplying all these numbers together gives you about 0.0002. So this is a very low probability that if you get this call from John, that it's true that John called, Mary didn't call, the alarm is going off, but it's going off for no reason. So you should infer that there's, given a call from John, that most likely the alarm is going off, and it's going off for a reason. Either there's an earthquake or somebody's breaking into my house. Of course, what you might want to know is what's the probability that somebody's breaking into my house and it's not an earthquake. In order to do that calculation, we just need to replace the probability of not B with the probability of B. But also note that A depends on B. So if we're assuming B is true, we need the probability that the alarm is going off and B is true, but E is false. So we're in the second row right here. So the probability of A given B and not E is not going to be 0.001, but rather 0.94. And we're assuming B is true, so instead of 0.99, this is going to be 0.001. And then now we still have the probability of not E. So doing that calculation would give you the probability that there is somebody breaking into my house. The alarm is going off. Mary didn't call, but John did call. Now, using Bayes networks, using this way of thinking, there are two important patterns of causal reasoning that I want to alert you to. So the first one, let's just start with this question. When there are two propositions that are correlated, so somehow we recognize that their probabilities depend on each other, must the event described by one cause the event described by the other? Must there be a causal relationship? Well, there's a classic example from the philosopher of science Hans Reichenbach. Suppose that there are two geysers which are not far apart and they spout irregularly. So we have these two geysers spouting water at random times. But you notice that they throw up their columns of water always at the same time. So the probability that one geyser is spouting water probabilistically depends on the other geyser spouting water. Of course, the inference you're going to draw is not that the spouting water in one geyser somehow causes the second geyser to spout water, but rather that there must exist a subterranean connection of the two geysers with a common reservoir of hot water. That becomes certain. So the fact that there's a common cause becomes certain. Here's another example. The size of a child's foot and the reading ability of the child are, of course, positively correlated. The larger the foot size, the higher the probability that the child has higher reading ability. And higher reading ability tells you something about the size of the child's foot. But of course, we don't think that the size of a foot has any causal relationship with the reading ability, or the reading ability has any causal relationship with the size of the foot. Rather, these two events are going to be independent given a common cause, and the common cause, of course, is the age of the child. So even though the child's foot size and the reading ability are probabilistically correlated, we don't think that that implies that there's necessarily some causal relationship between the two. Rather, we think there must be some common cause. And in this case, it's easy. It's just the age of the child causes both the foot size and the reading ability. So we can think of this as a principle of common cause. When events of outcomes are probabilistically correlated, then either one causes the other, or they must have a common cause. And we have a term for what happens when you recognize that there is, in fact, a common cause. So we say that P screens off P from Q when P is unconditionally dependent on Q, but independent of Q, conditional on both R and not R. That is, we say that P screens off P from Q when the probability of P given Q is not equal to the probability of P. So Q lowers or raises the probability of P, but conditional on R being either true or false, the probability of P given Q and R is equal to the probability of P given R. And the probability of P given Q and not R is equal to the probability of P given not R. So basically the idea here is we have P and Q, and they seem to be probabilistically dependent, but conditional on R, P and Q are in fact independent. And this is the information you should infer when there exists a common cause. When you have a Bayes net that looks like this, P and Q may be dependent, but conditional on R, P and Q are going to assume to be independent. There's a second pattern of reasoning that's important, and that pattern of reasoning shows up when you have two causes of a single event. And this is called explaining away. And this is a type of causal reasoning that's often employed. So the idea is that different causes of the same effect can interact. So rather than giving an abstract definition, let's just think of an example. So here we have a situation where we're looking at the ground and we see that the ground is wet. So W is true when the ground is wet, false otherwise. R is true when there's rain and false otherwise. S is true when the sprinkler is on and false otherwise. Now both the rain can cause the ground can be wet, but the sprinkler can also cause the ground to be wet. Now, observing that the sprinkler is on and that the ground is wet. So you see that the ground is wet. You don't know why the ground is wet. But observing that the sprinkler is on explains away the need for R to causing the ground to be wet. So observing S and W might actually lower the probability of R. And that's because you've explained away the need for R to cause the ground to be wet. Because you know for a fact that the ground is wet because the sprinkler is on, because you've actually observed that. So this would represent a situation where the probability of R, given the sprinkler is on and the ground is wet, actually lowers the probability of R. And this effect is what's known as explaining away. You explain away the existence of one causal factor because you observe another causal factor and you observe the effect.